common sense says, if I want to, I can hit them both the same. You can't. You can never hit a piece of paper as hard as you can hit a brick wall. A brick wall has a lot of mass. A brick wall is attached to the ground, isn't it? The ability of the brick wall to push back is huge. I don't believe you. Well, go hit a brick wall with your hand. Why is your hand bleeding and split open? Because the brick wall hit your hand really hard. How come when I hit a piece of paper, my hand's not all bloody? Paper did not hit me very hard, did it? All right, so you okay on number one? Now, action-reaction pair of forces are equal in magnitude. That's true. I touch you a little bit, the table touches me back a little bit, doesn't it? But they're always opposite in direction. Pretty easy? Is that pretty easy so far? Next, an action-reaction pair of forces can never cancel each other out. If they belong to the same pair, they can never cancel each other out because they never act on the same object. We saw this picture in the handout sheet. Now, what I'm going to be doing is we're going to do some force diagrams today, and I might say something like this. Identify force A1. Identify force A1. And the force is always drawn not on the object that created it, but what it's acting on. I know it's acting on the nail, but who do you think created that force right here? Who created that force? The hammer, right? So if I say, identify force A1. Okay, hammer, instead of saying axon, we say push or pull, right? Hammer pushes nail down. That's easy. The next thing says that action-reaction pair of forces have to fit a recipe. If you say A acts on B, then the next thing you say is B acts on A. Identify A1. Hammer pushes nail down. What's the recipe say about that force? What about A2? At the same instant that that's created, another force is created, isn't it? How would you identify that one? Sarah, help me out. You're way back there. Identify A2. And it has to fit the recipe. Say it again. One more time. Okay, so the recipe said A acts on B. Watch. A acts on B. You should say B acts on A. Right. The nail is who's actually pushing the hammer up, isn't it? Yes, no? Which one's greater? Which one's greater, A1 or A2?
Neither.
Okay, if you said that very quickly, you understand they cannot be different. They cannot. Now here's what's you got to fight in this chapter. Number 4. You have to fight this. Two objects can have equal forces acting on them. Okay? That should be acting. Two objects can have equal forces acting on them, but they can have different results. So you think if they had equal forces, the same thing is going to happen to both objects, and that's not true. For example, what was the nail doing before the force was applied to it? It was just sitting there, wasn't it? And then all of a sudden, a net force that way was applied to it. What's it have to do? Newton says, if you have a net force going down, what are you going to do? Starts with an A. Accelerate. That's another question I'll ask. I'll say, what effect did A1 have on the motion of the nail? What was the effect of A1 on the motion of the nail? Ready? What did he say? What did A1 do to the motion? What effect did it have on the motion of the nail? It what? Accelerate the nail which way? Down. Okay, now, what about this one? What effect did A2 have on the motion of the hammer? Or you could have said decelerate the hammer, or you could have said what? Accelerate the hammer upwards. Now, can I ask you this question? The same magnitude force, but he had different results. One accelerated downwards at a great acceleration, and one was decelerated, but it wasn't huge. Why was the deceleration not huge? Why was the acceleration on the nail bigger than the acceleration on the hammer? They both got accelerated. One of them accelerated at a huge acceleration, and one was decelerated not so huge. Eli, you look like you're thinking about this, so I bet you can tell me. We know that one reason why the effects are not the same is one was sitting still and one was already moving, right? I was moving down, the acceleration was up, it slowed me down. What's another reason why the acceleration, the effect looks different? You know.
The effect looks different on each object?
The forces were the same, but the effect was different. One reason is that one of them was moving, one wasn't. What's the other reason?
Resistance below the nail.
What's the other reason why the effect might be different?
Well, there's like wood below the nail, so it's not gonna.
Okay, that's another question. Okay, not counting, not thinking about the wood right now. Okay.
Okay.
How about this right here? You know?
Yeah, different masses.
What does that mean?
Well, the force was held constant, and if the masses are different, the acceleration.
So if the mass of the hammer is huge, then what's the acceleration on the hammer?
Little.
Small. What if the mass of the nail is small?
Big acceleration.
Ah. So you have to know a little about Newton's second law to understand Newton's third law, don't you? Okay, anyway, that's down here. What effect did A1 have on the motion of the nail? It accelerated it downwards, didn't it? What effect did A2 have on the motion of the hammer? It decelerated the hammer, didn't it? All right, so as we get ready to start to draw these, they're called force diagrams. And I'll have you do some of these, but let's take a look. Yesterday, you saw me stand up there and push against the wall. And I said, I started pushing the wall that way, didn't it? Now, what happened at the exact same instant? Teacher pushes wall that way. Wall pushes teacher that way. And my question to you was, number one, how come the teacher is not going that way? If there's a force on me in that direction, I should be accelerating in that direction. What was the answer to that? And I know who answered it, so I don't want that person to answer again. But if I push on the wall, then how come I don't go that way?
Because the wall pushes back. One pushes.
Okay, and so what? So what does that mean?
That wall has.
Do they cancel each other out?
The wall doesn't.
Wait a minute, listen. Do they cancel each other out?
No.
What do you think? I can't hear. Wait, Parker, I can't hear. That's right. There's another set of forces involved in there. So be careful. The trap you're going to fall into, don't fall into it, okay? Don't tell me. When I push on the wall and the wall pushes me back and I don't go anywhere, don't tell me I didn't go anywhere because they cancel each other out. An action, they're part of the same action-reaction pair, they can never cancel each other out. Why? Because one of them acts on one object and the other one acts on the other object. They're not even acting on the same object. So don't tell me I don't go anywhere because those two forces cancel each other out. They can't. One of them acted on the wall, one of them acted on me. But if you draw a force diagram, the tail, I'm going to ask you again to do this, the tail of the vector is drawn on the object that it's acting on. You get that? So identify A1. Try that. Identify A1. Walker, you do it. Identify A1.
How much force that has?
Yeah, identify it. Here's A1 and here's A2. Identify A1. We did that on this sheet. Okay, I just got done doing that. All right, I'll give you a break. I'm gonna call on somebody else. You come back, okay? Patty, identify A1. One more time. All right, person, say it again. A person pushes wall to the right. Okay, now identify A2. And I told you the entire chapter is right there. If you said person pushes wall to the right, then the recipe says how do you do A2? That's to the left. Everybody got that? So I've identified A1 and A2. Now, you would think that the teacher, the person would start accelerating that away from the wall, but he doesn't. So let's find out what happens. As soon as the wall starts pushing me this way, what happens to my, look at this, I have the wall, the person, and the floor. I should have a pair of interactions here and a pair of interactions here, shouldn't I? As soon as the wall starts pushing me back, my feet start pushing the floor which way? Here, identify B2. Jeff, you can do it. Identify B2, Jeff.
The wall,
No.
the floor,
Identify B2.
the dude's feet
Dude, okay.
getting pushed.
Dude pushes floor to the left.
Yeah.
Okay, now identify B1. B1. It's all right here. Do you have this paper with you? It's all right here. It fits the recipe, doesn't it? One more time.
So
Dude pushes floor to the left.
the floor pushes dude.
All right. Now, have we identified the four forces?
Oh.
Now the question is, why doesn't the person actually accelerate? Because what? Because what? What? All right, watch now. This does take a different mindset, but I want you to think about this. Ready? Don't look at the wall. Don't look at the floor. How many forces are acting on the dude? Two. Now, are they part of the same action-reaction pair? They can't be. Does A2 cancel out B1? Yes.
Wait, where's A2?
A1 can never cancel A2. A1 can never cancel A2 because they never act on the same object. But can A2 be canceled by something like
I
B1?
see A2.
And that tells me why the dude doesn't go anywhere. And what's interesting is, if I could at least eliminate a little bit of that, I can't eliminate friction right now. I don't want to put oil in my shoes. But if I eliminate part of it, and look what happens. I actually do. In that case, what happens? Which one's greater, A2 or B1?
A2.
Hey, I need your attention, okay? Which one's greater when I just did that? A2 or B1?
A2.
A2.
Oh,
There had to be a net force in that. Wait, how did I know there was a net force in that direction? Didn't I start accelerating? I started accelerating in that direction. So in that case, A2 must have been greater than B1. Now, let's be careful. The hammer and the nail again. Which one's greater, the force of the hammer on the nail or the force of the nail on the hammer? Which one's greater? It's all right there. Which one's greater, the force of the hammer on the nail or the force of the nail on the hammer? Ben,
Wouldn't they just be the same?
they have to be. They have to be the same. Aren't they part of the same action-reaction pair? Didn't he say that?
yes.
For every action equal, isn't that Newton's third law? They have to be the same. Now, the effects aren't the same because this object was sitting still and all of a sudden it starts accelerating downwards. This object is already moving this way and the net force was up, wasn't it?
Yeah.
So it slowed it down. Another reason, the acceleration on the nail should be greater. Not the force of the nail. The acceleration of the nail should be greater because it has what? It has a tiny mass. It's going to have a lot of acceleration. What about the acceleration on the hammer or the deceleration?
Small.
It's going to be really small. Now, if you start thinking like this, you should be able to answer a lot of questions, okay? I want to show you another one. Here's another picture. Now you're not going to like this one either. Which one's greater? We said in many chapters that the earth is pulling on you, right? It's called your weight. Is that correct? The earth pulls on Kinsley. Earth pulls Kinsley down. Finish the recipe. Kinsley pulls earth up. That is correct. Now, if Kinsley is up here 10 feet in the air and she steps off, she's going to accelerate at 9.8 meters per second squared. And because the earth's going to pull her and accelerate, right? But when you step off that ledge, are you going to watch the earth come toward you? Why not? It is being pulled up. But what's the mass difference?
It's just.
Unbelievably huge, right? The amount that it accelerates upwards is unbelievably small. We can't even measure it.
So why did every human on the earth jump?
That's a good question. That's a good question.
The earth?
If the problem is if every human jumped, would that push the earth back?
Let's do it.
Now, I will tell you, as we get through this chapter, okay, wait a minute. As we get through this chapter, we're going to ask some questions like that, okay?
Oh, really?
Okay, here's a question I have for you. Ready? On cartoons, sometimes they do this. Ready? See my hand? All right? I'm going to push this chair. And is there a force on that chair going that way? I should be accelerating that way. And we're not quite ready for that yet, but we're going to talk about that. If you fall off a cliff, why don't you just put your hand on your back and push yourself back up? And we're going to talk about that later, okay? But there's some great questions you had. I will tell you one thing. What if Kinsley was the size of the moon? If Kinsley was the size of the moon and it fell off a 10-foot ledge, then not only would the moon accelerate toward the earth, but you would actually... if you weren't on the earth, the earth would actually visibly accelerate toward the moon. But right now, the mass difference is so huge, no one is going to feel or even be able to measure that the earth is being pulled up by you. All right, down here. Which one's greater? The force of the cannon on the cannonball or the force of the cannonball on the cannon?
They're the same.
They have to be. Now, what effect does the force on the cannon have on the motion of the cannonball? What's it going to do to the cannonball? The motion of the cannonball. And don't say goes. That's something a fifth grader tells me. It's going to accelerate with a huge acceleration, isn't it?
Yes.
And what happens to the cannon?
It goes backwards.
It's going to accelerate
Not
No,
nearly as much.
it's going to accelerate backwards.
backwards
Big mass.
because not as much because of what?
Big mass.
Big mass.
That's right. I did that the other day. I went and I said, "Can I have a quarter pounder?" But can I have? I said, "Can I have some a Big Mass sauce?" I said, "They said they, no, not Big Mac sauce, but Big Mass sauce."
Big mass.
All right. Now, what we're going to do is I'm going to try to tell you today about something that I thought I knew. I really thought that Newton's third law was so simple that there's no way I didn't understand it. If somebody told me, hey, do rockets work because of Newton's third law? I say, yes, of course. And I thought I understood it. Uh-oh. Wait a minute. I thought I had one here. Let me go get a balloon.
Side by side. Would that make it work?
I couldn't imagine.
And then we all get the humans at the same time. We
You know
go,
how like we got you know how like they got everybody to storm Area 51? We just get everybody to go to Arizona and jump.
All right, here we go. So let's look at this right here, okay? I'm going to go ahead and take my mask off for a minute. All right, so let's pretend that I tie a knot in this, okay? Let's just pretend I did tie a knot in this. I don't want to do that because it's hard to get it out. Let's pretend I have a knot in there and it's sitting on the table. All All right, what's the net force on the balloon? 0. Okay, now, let's think about this. Air inside the balloon pushes the balloon that way, and that way, and that way, and that way. Does everybody get that? Now finish the recipe. Air inside the balloon pushes the balloon that way, and that way, and that. See that? Finish the recipe.
Force pushes air. Pushes air.
Colleen, you can do it. Fits the recipe. Air in the balloon pushes the balloon that way.
And then the balloon. Oh,
Well, Colleen.
Okay, recipe. That's right. And the balloon pushes the air that way, and that way, and that way, and that way. So guess what? If you add up all the vectors on the balloon, this one, and that one, and that one, and that one, what's the net force on the balloon? Imagine I had a knot on here. What's the net force on the balloon?
0.
0. That's why the balloon is not accelerating. What about the air in the balloon? The balloon says push you in, push you in, push you in, push you in, push you in. And there are a lot of things that cancel in there, aren't they? What's the net force of the air in the balloon? 0. And that's why a balloon with a knot in it the air doesn't accelerate, the rubber balloon doesn't accelerate, but when I let go of this, something's going to happen.
Whoa.
So when I let go of that, something very important happened.
It pushed the air and then
No, wait.
escaped.
Think about it.
I thought about it.
When I let go of that, was the air in here, was air still pushing the balloon this way and the balloon pushing the air this way? Yes. Yes, yes, yes. But
it pushed out this way.
But the most important part of a rocket, that's what that was, a little mini rocket, is the hole. When you have a hole, then there is no force pushing the balloon down. The balloon part's gone. So what is the net force on the balloon? Push, cancel. No cancel. Nobody canceled me. So when I open this hole, the net force on the balloon is up. Now, think about this. Inside the balloon, the air inside the balloon, there are a lot of forces being canceled. But the balloon pushes air down. It used to be canceled. But now there's a hole there. So what's the net force on the air in the balloon? What direction?
Up. Oh wait.
Down and out.
Down.
Toward the
Whichever
hole.
way is out.
Toward the hole. Now, the misunderstanding is this. I have air in the balloon. I have balloon, and watch. Okay? One more time, watch. And I have air that's already left the balloon. Now, here's what happens. Here's the problem. A lot of science teachers do this, and they do this wrong. They'll say the air that comes out, the air that's already out of the balloon goes that way, and that makes the balloon go that way. There's something technically wrong with that. It doesn't fit the recipe, does it? So I have air in the balloon, I have air that's outside the balloon, and I have the balloon, don't I? Ready? Watch. Air coming out of the balloon pushes the air in the room that way. Air in the room pushes the air coming out of the balloon that way. Okay, I get it. So the air in the room should accelerate that way, and the air coming out of the balloon should what? Say it. Starts with a D. Decelerate. And it does. But you know what's missing? Balloon. That's not the action and reaction pair that makes that balloon go that way. It's not here. It's in here. It's in here. As soon as I open that up and make a hole, there's a net force that says force the air toward that hole. And when you force the air toward that hole, then what happens to the rubber balloon? It moves away from the hole. So remember I talked about rockets, and that one time, and I was taught wrong. I said, rockets demonstrate Newton's three laws? Yeah, third law, yeah. Okay, how is it? Well, you know, the exhaust gases that come out of the rocket, they push against the launch pad. And they push it that way. And the rocket goes the other way. And see, I'm smart, aren't I? I thought I was smart. I found out later, what word is missing? Watch now, ready? Exhaust gases push on launch pad. Finish the recipe.
Launch gas.
Launch pad pushes exhaust gases up. Wait a minute. What's missing there? Rocket. Now, again, when I was first teaching, somebody asked me, what happens when it gets away from the launch pad? I said, well, and I thought I was pretty smart when I said this, exhaust gases push on the air in the atmosphere. And that makes the rocket go in the other direction. Let's try for real. Here's what really. Exhaust gases do push on the air downwards, right?
Yeah.
And the air does what? Pushes on the exhaust gases, right?
Yeah.
But what's missing? Rocket.
Yeah.
Neither one of those is why the rocket is moving. Because one time, remember I told you I paused? A student asked me very, very early ago, 45 years ago, they said, do rockets work in space? And all of a sudden, what I thought I knew the answer, I was wrong. Because I couldn't understand that. I knew rockets worked in space, but there was nothing for the exhaust gases to push against. That's where I was wrong. You see that? The action-reaction pair is like this. Okay, now stay with me, all right? This is important to me, because you understand how this works. Okay, inside this rocket engine is a thing called a combustion chamber. And they make this combustion chamber very strong. Why? Remember the piece of paper? Which one can you hit harder? A piece of paper or a brick wall? What kind of combustion chamber will be able to push back more? One that's made weakly or one that's made rigid and strong? And so the combustion chamber is very, very strongly made, all right? So watch right here now, ready? Watch. The chemical reaction takes place. The gases expand. The gases expand and they do what? Identify force A1. Combustion chamber, gases push combustion chamber wall that way. And identify A2. Help me out. Here. Gases push combustion chamber that way. Combustion chamber pushes gases that way. Now watch over here. Combustion expanding gases push combustion chamber that way. Let's call that B1. B2. Combustion chamber pushes what? Expanding gases that way. Now watch. Can A1 ever cancel out A2? No. But can A2 be canceled by B2? Yes. Cancel. 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 As long as this thing is not open, once this is closed and then the pressure's building up, the rocket's not going anywhere. When they're ready to go, then this opens up, right? Now, when that opens up, here's what happens. When it was closed, gases push combustion chamber up, but combustion chamber push gases down. Now here, when it was closed, combustion chamber pushes gases up, blah, blah, blah. These two are gone. They're gone now. There's a hole there, right? So now, which ones don't get canceled? Which force does not get canceled? This one. And so what happens to the combustion chamber? It starts accelerating away from the hole. Get it? And what happens to the gases in the combustion chamber? Not the ones that have left, not the exhaust gases. What happens to the gases in the combustion chamber? Which way are they going to be accelerated? Oh, I lost you on that one. When the balloon was closed, there was no net force on the gas in the balloon. There was no net force in the balloon. Everything got canceled, didn't it? When I opened it up, what happened? When I opened it up, I still had this one and these, right? But I didn't have these two, did I? So this one used to be canceled by this one. It's not there anymore. So what is the net force on the balloon is to move away from the hole, accelerate away from the hole. What about the gases in the balloon? Start accelerating what? Where? Accelerate toward what?
The whole.
Toward the hole. In space, in a combustion chamber, get it? I don't need anything outside to push against. The push is inside the combustion chamber, isn't it? When the gases expand, and I got a hole here, that when they expand, the net force is to drive the combustion chamber away from the hole and drive the gases toward the hole. Everybody see that? Now, is it true that exhaust gases push on the launch pad down? Yes. Does the launch pad push gases up? Yes. Does that have anything to do with the rocket? No. That action-reaction pair does happen, but that's not why the rocket works. Otherwise, it would never work in space. It had nothing to push against outside the rocket. I want you to let that sink in a little bit, okay? I want you to think about that, and it's easy to tell somebody, all those exhaust gases are pushing against something, that makes the rocket go in the opposite direction. No, it's happening in the combustion chamber. You get that? Now, of course, the combustion chamber is attached to everything else. So if it goes away from the hole, then everything else goes away from the hole, doesn't it? All right. I hope you got a little bit out of this. All right. Let's take a look right here. Ready? Identify F1. MSJ, I haven't called you yet. Identify F1. Identify F1. Remember, in a force diagram, the vector is drawn, the tail of the vector is on the object that it acts on, not the object that created. MSJ, identify F1. Don't look. I'll give you a clue, okay? If it's drawn on the football, don't say the word football first.
So the foot is exerting force onto the football, so it's pushing it down.
Okay, foot pushes football to the right. Everybody got that? All right, Walker, back to you. Identify F2.
Can't really see it.
It's a foot.
Identify F2.
The football is pushing back on the foot.
Pushes foot to the left, isn't it? Is that right?
Yeah.
What effect did F1 have on the motion of the football? All right, Jessica. What effect does F1 have on the motion of the football? Say it. Which way? Yes. To accelerate the football to the right. And that's what happens, isn't it? Go ahead, Jessica. What effect did F2 have on the motion of the foot?
It accelerates to the left.
But the foot's moving to the right. So if you accelerate the foot to the left, it's already moving to the right. What's the effect on the motion then? To decelerate the foot. Isn't that right? Yes? The effects, the forces are the same magnitude, right? But the effect is different. I was sitting still. I started accelerating to the right. I was already moving. And so that caused me to slow down, didn't it? To decelerate. Look right here. Ready? Everybody ready? Identify, let's do, okay, here's F1. F1, we already did that. Foot pushes ball to the right. F2, ball pushes dark foot to the left. Next, L1. Light-colored foot pushes ball to the left, and the next one is ball pushes light-colored foot to the right. Okay, now, why does the ball not go anywhere? Why does the ball not go anywhere? Alistair, I haven't called you yet. Why does the ball not go anywhere here? And give it to me in terms of symbols. This is F1. This is F1, and this is F2. This is L1. L1, this is L2. Why didn't the foot go anywhere? I mean, the football.
Because the force from this foot.
Give me a symbol. Which force are you talking about?
Oh,
Both your feet to show
F1, the inward force on the white foot.
F1.
Size F1, okay.
F1 is from the dark foot.
Okay, F1 counteracts the.
Counteracts.
The force from the other foot.
F1. All right, one more time. Remember when I was pushing against here and I said, which direction is the net force? And you said it had to be there. That means that force there was greater than another force. Tell me about F1 and L1. Say it again. They must be equal, shouldn't they? F1 would have to be equal in magnitude with L1, and they're in opposite directions, right? They cancel each other out, but they're not part of the same action-reaction pair, are they? If you're in the same action-reaction pair, you never cancel each other out because you never act on the same object. That kind of diagram is what I need you to understand, all right? I want you to put symbols on it. I want you to understand it. Now, what I'm going to do is I'm going to introduce you to probably one of the hardest parts of the chapter, but when you get it, you feel very proud that you finally understood it. And it's the last part of the chapter right here, and it starts out with a cartoon. Ready? See if you can figure out which parts of this cartoon are true and which ones are there's some falseness to it. Ready? Giddy up! Pull that cart so we can get going. For me to pull the cart would be a futile effort. You see, if I pull on the cart will pull back on me. True or false?
True.
Okay. By Newton's third law, the forces are equal and opposite. True or false?
False. True.
That's true.
Yeah.
So they will cancel out and get a zero net force. True or false?
Wait.
They can't because they can. But he says they'll cancel each other out. So guess what? Even if I start to pull in the cart, we won't go anywhere. And a farmer says, physics, I figured I don't care about the force exerted on you. I'm interested on the force you exert on the cart. You pull that cart, and I guarantee we'll move. But how can I move forwards when the cart pulls back on me? You got it yet?
True.
Now watch what he does here. Watch. He finally figures it out. Just push backwards on the ground. And by Newton's third law, the ground will do what? Push you forward equally, and I'll just simply follow along with you. And he says that ground is doing a very good job. When you leave today, every step you take, when you leave today, thanks, floor. Thank you, floor. You're going to push the floor backwards. And what's the floor going to do? Push you forward. You won't leave this room unless the floor pushes you out of this room. You don't like that. If I put vegetable oil all over the floor, you won't be leaving the room because the floor won't be able to push you out of this room. So what happens is, I'd like you to read this. Okay? And I know tomorrow is for a reactometer, but Thursday when I come back, I'm going to give you a smaller project for next week, and it has to do with the horse cart problem. Now, I'm going to show you something. When you read this, the one thing the author, and I love the author's book, the one thing I think he made a mistake here. Your book doesn't have all these letters on. I put them on there, doesn't it? If you want to read this story and put the same kind of a letter with subscripts, like you can have A1, A2, B1, B2, C1, C2. But make sure you know who the same action-reaction pair are, all right? Get that? And then if you do that, I'll come and explain this to you. I'll explain this to you on Thursday, and then you'll have a little project to do for maybe Tuesday or something like that. It's a paper and pencil project. You'll like it a lot. I'll even show you. I only have about 3 minutes to go. I'll have you getting. I know you're still doing a reactometer, but let me show you some of the ones I've kept from. I can't keep them all. I'll just show you some of the ones I've kept for the many years I've done this. And you'll get a paper just like this. And what you're gonna do is, you're gonna draw a horse cart problem, but you can't use a horse in a cart. But it has to represent the same forces that are in the horse cart problem. Okay, here's one. Okay. Here's one that's very, very old, very, very old one. Very, very old one there. Here's one. Okay. Here's one. Drew Rennie. You might know, maybe you remember, she didn't graduate that long ago. Here's one. Somebody like trucks and a skateboarder. There are actually two Lydia Thompsons at this school. This is one of the Lydia Thompsons. And you'll see,
That's, I was gonna say, I kinda
here's one who obviously liked Calvin Hobbes. Here's one, Abby Lynn.
It's like Jeffrey.
And you'll see all these different arrows. See the arrows drawn?
Yeah, it's like a waterway class.
And here's one who they have told a little story. Their little weasel had a story to tell. This one, Winnie the Pooh. This is, I think this is supposed to be me, but somebody like Ozzy's ice cream. Here's it's pretty.
Who did that?
Isabella McClellan.
That is a very,
What? Jeffrey?
Here's her mother is the art teacher in elementary. This is Katie Butler. Katie Butler. This is one from way, way long ago when I used to teach at many years ago at Grimsley High School. I had a mustache until about 20 years ago. Anyway. Okay, and oops. Here's one from a student many, many years ago who actually ended up going to Yale from Grimsley. And she had a whole story, and she had me in there, and she even had a little story about it. She made a rhyme. She made a poem out of it, and at the end of the poem says, "Don't put Descartes before the horse." Ooh, and that happened to be a 9th grader. Wow. Here's one. All right, how about two more? How about more than two more? Yeah. This was before I required color.
I like that.
Here's somebody who likes Rottweilers and meat.
That's a Rottweiler.
Rottweiler, what did I say? Rottweilers? Okay. Here's a Grinch. That was okay. I'll see you later. All right, see you later. Hey, bring your stuff. Bring your stuff tomorrow, okay?